Hi, I'm Zor. Welcome to Unizor Education. Well, today we will continue talking about extremely important Noether Theorem. We did cover a few special cases, like conservation of energy, conservation of momentum, conservation of rotational momentum. Today I would like to start talking about a general case. Basically, that's the way how Emmy Noether did it herself, as a purely mathematical theory, which resulted later on in application to physics. It's actually two lectures. This first lecture, we will cover the way how variables involved in the motion are changing as a result of the motion. And then the next lecture will be basically the proof of the theorem itself, using whatever material will be presented today. Now, this lecture is part of the course called Physics Plus for All. It's presented on Unizor.com. It's a totally free website. There are no advertisement, no subscription. You don't have to sign in if you don't want to. And sign in is also just email, which very rarely used. So it's a totally free, knowledge-based, which you're welcome to use the way you want. It also, Unizor.com also contains other courses which are actually prerequisite for this one. You have Math for Teens and Physics for Teens. They cover a lot of material. So right now I'm assuming that whatever was before in this chapter of the Physics Plus called Lagrangian is known to you. These are a bunch of lectures which preceded this one, and obviously I'm going to use all this material. Alright, so let's start. First of all, what was the main result of Noether's theorem? It's the conservation law, a relationship with certain conditions on Lagrangian. Lagrangian is basically concentrates in itself the laws of physics, in as much as Newton's laws were, kind of quintessential for classical physics. This is just another view, which is more general and more applicable to other areas of physics, not only to classical mechanics. So we are talking about Lagrangian's property, which are not supposed to change as something changes. Now, what something is changes? It's related to motion. When the motion happens, your time is running, your coordinates are changing, your velocity is changing, and these are three major parameters Lagrangian depends on. Remember, Lagrangian is a function of optionally time, the coordinates, and velocities. So we have to know how the motion affects these major components of Lagrangian, and that's what will be in this particular lecture. Next lecture, I will use it to basically derive the laws of conservation from it. Okay, so motion is changing all these coordinates and times. How can it be mathematically represented? And here is how. This is our time. Time is changing, right? So the change can be characterized by some parameter. So what we are doing is we are introducing a function which depends on time and coordinates, and that would be a new time, and I will put epsilon, where epsilon is a parameter, and I'm using the letter epsilon because in mathematics it's usually associated with infinitesimal value, and we do need actually the dependency of how time will infinitesimally change during the very small motion. Okay, so that's basically the way how we represent the time as a mathematical model of motion. Now, similarly, we can represent our coordinates as function, and I will do these coordinates in generalized coordinates. It's basically n different numerical parameters. So I'll put index I, which basically changes from 1 to n, where n is the number of degrees of freedom of our system. So that's also a function. So we have one parameter, epsilon, which basically tells us how time and generalized coordinates are changing as a result of motion. Now, we don't really have to talk about motion right now. Motion is physics, and we're talking about mathematics. So just consider that these are functions or families of functions. For each epsilon, we have some kind of transformation. For each epsilon, we have some kind of transformation of time and transformation of coordinates. So epsilon is a parameter of transformation. Now, these are transformation functions, obviously. Now, if in the past coordinates were functions of time, and I mean each one coordinates, obviously, then after something is changed using our transformation of all coordinates, new coordinates would be new coordinates as function of new time. So that's what's very important. And that might be a different kind of dependency, obviously, as a result of motion. So change of coordinates right now is something which is the most important part. Let's not talk about motion. Just consider that this is purely mathematical family of transformations. And the family means that epsilon can be basically any parameter. We do consider this basically in the future that it would be in infinitesimal value. But so far it's just parameter change. Now, what we are interested in is how fast these parameters are changing. What does it mean, how fast? Well, it basically means that we have to know dt by d epsilon and dq by d epsilon. And this is very easy. This is just basically dt by d epsilon, and this is dqi by d epsilon. D epsilon. So that's not difficult, and we can use these changing of these derivatives as the base which explains how time and coordinates are changing with time, and then we can substitute it into Lagrangian, and Lagrangian depends on these new coordinates. The problem is velocity. Velocity is a problem because what is velocity? How velocity is changing? Velocity is dqi epsilon by dt epsilon. That's what velocity actually is. And it's not easy to differentiate this thing by time, because time depends by modified, by transformed time. So the problem is here. So if the time is not changing, so if the function t of epsilon, t and q is identity, which means t epsilon is equal to t, then there is no problem. We will just differentiate this, which is just differentiation of the function q by dt. but differentiating by divided by differential of transformed t is kind of a problem, purely technical problem. And the rest of this lecture is actually the way how we can represent this thing in a more palatable kind of a format. So in the next lecture we will be able to use it as a component of Lagrangian, because Lagrangian depends on time, the coordinates, generalized coordinates, and their velocities, their derivative, time derivative. And that's what time derivative is, and without this one we cannot actually continue. So the most important part of this lecture is basically derive this expression in a better way. Okay, so let's just do it. It's pure math right now. So let's just forget about all this. This is all kind of obvious. And we will try to manipulate this as much as possible. A couple of words about this parameter epsilon. Epsilon characterizes the how exactly the transformation is done. Now, we would like to have this transformation to be, well, nice in some way. In mathematical lingo, that would be that these transformations are supposed to make up a group, more precisely the Lie group. What I actually mean, for example, if you transform this into, let's say, alpha, and then that would be transformed into beta using another transformation function. So in this case epsilon equals to alpha, and in this case epsilon equals to beta applied to already transformed by alpha. It's supposed to be equivalent to t transformed to alpha plus beta. That's what actually most important qualification of this family of transformations is. Now, same thing with qi, obviously. Alternatively, if beta is equal to minus alpha, it means I will transform by alpha and then transform by minus alpha, and if we are talking about nice transformation, we should return to the same original thing. So t of 0, which is alpha minus alpha, whatever, it's supposed to be equal to t from which we started. So these are properties which make this family of transformations a Lie group. Lie is just the name, Lie. L-I-E. I think that's how it's spelled. All right, so these are just nice properties of our transformation functions, which are needed for our purely technical derivation of. So again, our purpose is this is Q. Our purpose is express Qi of epsilon by d t of epsilon, and then later on find out how it's changing with change of parameters, which is a derivation of this as well. All right, so let's start. First of all, this dqi divided by dt epsilon. Now, since qi is equal to this, so differentiation by dqi epsilon by dt epsilon can be represented as differentiation qi by dt divided by dt epsilon by dt. I have to change this. Okay, this is just a divide by dt both sides, and now it becomes a little bit more palatable because now I can differentiate it using the full derivative formulas. So what is this with derivative formulas? Well, derivation derivation by partial derivation by epsilon times times derivative of epsilon by dt. Well, epsilon and t are independent from each other, so obviously the first member is equal to 0. Now the second member, t, differentiation of t by t would be 1, right? And the third member is partial differentiation by q times q by dt would be actually plus, and that would be a sigma, yes. Q basically represents q1, q2, q3, and we have to really do it with one, with the second one, and the third one. That's why I put sigma by I. Derivation of q qi by dq k sample k. Now we have this I, that's why I put this I here. But since inside you have all these, so k is index of different q, q1, q2, q3, times differentiation of qk by t, by dt, which is what? That's that's original speed, right? So I can put qk prime. Prime means different time differentiation, regular time differentiation. So that's basically the numerator. The denominator would be very similar. Again, forget about differentiation by epsilon because it's not dependent on t. Now the differentiation of t by t one second. I have to put this. Made a mistake. I forgot. Differentiation of q I by dt times 1. Plus. And here we have differentiation of dt by dt times 1 plus similar thing. I have to put sum of k dt by dqk times qk velocity. All right. So differentiation by epsilon doesn't make sense because epsilon by t would be 0. Differentiation by t, that's the 1, times differentiation of t by t, which is 1. So basically that's the final formula. I can scratch this one. Don't really need it. Okay. Now, is it better than this one? Hard to say. And since our final goal will be differentiation by epsilon, and t and qi are all functions of epsilon and t and q, so differentiation of this would be really messy. So we will try to manipulate it in some way. Okay, so what's our next manipulation? Well, first of all, we do assume that epsilon would actually be infinitesimal value, because we are really need something which is just a little bit changing, because we need the velocities. So velocity, instantaneous change of velocity, because this is the change of new velocity. It's actually supposed to be just near the point where we started. Okay, so how can we do it? Let's do it this way. since we are assuming this, we can use something like formula, Taylor's formula, where if you remember, if you have, let's say, y of x, y of x can be equal to y of x0 times dy by dx at point x equals to x0 plus some kind of a one second, that's supposed to be plus times delta x. Remember this? Plus the faster going to 0. If delta x is equal tending to 0, that would be an infinitesimal of a higher order. So this is basically a result of the Taylor's formula. Now we will use the same thing. So if you are deviated from x0, then the deviation is actually multiplication of deviation of argument times derivative at this particular point. We will do exactly the same thing. So my new value would be t epsilon, my old value would be t, and so I can put it this way. My t of epsilon is equal to t plus the delta x, in this case it's epsilon, because that's basically how my my argument is changing, times dt by d epsilon at epsilon equals to 0 plus more the infinitesimal of higher order than epsilon. Am I right? Let me just think about it. Probably more appropriate would be a partial derivative, because we don't really need to differentiate by its partial derivative here. So t and q are fixed, so we don't really need them. So only epsilon is changing. As epsilon is changing, t goes to t epsilon, and the difference between them should be proportional to epsilon times partial differentiation of this function plus infinitesimal of a higher order than epsilon. And same thing with q epsilon I. It's qi plus epsilon dqi by d epsilon at point epsilon equal to 1 plus infinitesimal of a higher order than epsilon. Now, why do we need this? Because it's much easier to differentiate something related to just plain proportional kind of functions. And since we are differentiating even more by epsilon, this thing would not actually be involved. So, from this, let's do it this way. I would like to, okay, we don't need this. That was just an example. This is a very important thing. We will call this xi. No, that would be a time. Okay, time, I will use the letter tau. Tau of q and t. Capital T is function of epsilon, t, and q. When we are making a partial derivative by epsilon at point epsilon is equal to 0, we have a function only of q and t, and I call it this way. What is this? this is basically a reflection of how our time is the speed. This is the speed of change of time, rate of change of time, if you wish. And similarly, this would be Ci of qt. That's the speed or rate of change of coordinates as epsilon is changing. Because if epsilon is changing a little bit, my time can be changed a lot or a little. So basically, the partial derivative of this function is a rate of change of time with this particular transformation. And this is rate of change of coordinates. And they are called generators. In physics, they call it generators. Well, in mathematics, it's just derivative. But physics call it generators of time transformation. And this is a generator of, this one is the generator of coordinate transformation. And in this particular way, we can write our expression as T epsilon is equal to T plus this times epsilon plus little o of epsilon, and the Qi epsilon is equal to Qi plus Xi times epsilon plus all of this. Now that actually makes our life a little bit easier. And here is why. Because now dqi by dt, now qi is this, right? Now, to differentiate it by dt is kind of easy, because it's a partial differentiation by dt. So the only thing which is depending on time is our coordinate generator of coordinate transformation. So that basically can be expressed as dxi of qt by dt times epsilon. Epsilon is a constant in this particular case. I mean, it's not a constant, we are assuming it's infinitesimal, but it's not dependent on time. That's why partial differentiation by time is this one. And analogously, we have differentiation by qk. Now, what's differentiation by qk? dqi by dqk is equal to, again, only this one, so it's a dxi of qt by dqk times epsilon. Right? No, not necessarily. 1 second. It depends. We have this component. So I forgot, because if I is equal to k, we have to really differentiate this one as well, and it would be 1. If I not equal to k, that would be 0. So for all I not equal to k, this is correct formula. But if I is equal to k, when I differentiate by qk, that would be 1. So I will use a symbol, mathematical symbol, which is called delta ik. Now delta ik ik is equal to 1 if I is equal to k, and 0 if I not equal to k. So I will use this one plus my partial derivative. Okay, now it's correct. Okay, now time. Same thing in the denominator. We will have time by dt would be tau. No, it will be 1, because this time by time would be 1. So dt by dt would be 1 plus, and tau would be differentiated by time. Tau qt by time. Right? And epsilon. Yeah, I have to multiply by epsilon as a constant. And differentiation of time by dqk for this one. Okay, the first parameter is not dependent, so it's only tau. D tau of tq divided by dqk. Okay. So I will use these representation and put it into this formula. So what will I have? My numerator would be qi by dt, which is this one, and that would be this dxi by dt time epsilon plus sigma of these guys plus sigma by k delta ik plus dxi by dqk times epsilon. That would be my numerator, sorry. And here is how I will transform it. Now, if I is equal to k, so for one particular k, which is equal to I, that's 1. So if I is equal to k, I will basically have this 1, and the result would be, 1 second, let me just think about it. It would be only, okay, result would be xi by qi in this particular case. Okay, 1 second. Yes, I would like to take it out from this sigma for one particular case, and that means that, okay, let me just wipe out this one. dq okay, plus this one dqy by dqk delta plus epsilon. Okay, that's correct. So I put d plus dk plus sigma. Why did I put this one? Oh, that's my mistake. Epsilon only multiplied by this one. Okay, and this. And q k. Okay, yeah, I didn't really need this bracket, so altogether is in brackets like this. Okay, now I see. Now it's correct. Okay, so what does it mean? Now, if k is equal to I, this is 1. And let me just separate this multiplied by qk from the rest of this. So I will have dci by dt times epsilon plus. I will do it separately. Sigma of this times k. Sigma of delta I k by k times qk plus sigma of this dci by dqk times qk. It's a velocity. And this one is equal to, if k is equal to I, it's 1, otherwise it's 0. So we'll have only for one term, which is only qi. So that's what my numerator would be. And I will change slightly differently is I will put this epsilon dxi by dt and qi plus. That's what I will do. I changed the order and put epsilon outside of the parentheses. That's the same thing. Alright, done. Now that's my numerator. That's this one. You will see that this is much easier to deal with because it's proportional to epsilon. Now, same thing let's do with denominator. Denominator is this one. So it's dt by dt, which is what? This one. Okay, so it's 1 plus d tau by dt epsilon plus this one multiplied by qk. So sigma d tau by dqk times qk velocity. So now we have this. This is numerator, this is denominator. And what is this? What actually we were discussing? This is all q I epsilon. The I's velocity transformed by epsilon. So this is numerator and this is denominator. And now I can wipe out this. one small trick and we will reach our goal. Equals. Just to make the whole life a little bit easier, recognize what this actually is in parentheses. Well, this is d xi by d t. Why? The full derivative of xi, which is depending on t and q, is what? Partial derivative by t times t by dt, which is 1, plus sigma partial derivative by each qk, this is q1, q2, qn, times derivative of qk by time, which is this one, velocity, times epsilon. Here we will have a similar situation, 1 plus full derivative of tau by dt times epsilon. Oh, I forgot to put epsilon here. Now, why is this better? Well, here is why. It's equal to qi plus a epsilon, and this is 1 plus b epsilon equals 2. And I will just write the formula, and it's easier to check it. It's qi velocity plus epsilon a minus b q I plus of epsilon. So this is equal to this. Why? Well, if you will multiply this by 1 plus b epsilon, what would be? Q1, qi prime times 1 would be qi. Then it would be multiply e times a times 1 would be a times e. Now we will multiply by the whole thing by b e prime. Now if you will multiply q by b would be b q prime. And if you will multiply epsilon okay, let me just write it down. So this times this would be qi prime plus b qi prime epsilon, right? Now this times this plus epsilon. Now a times would be a plus ab epsilon minus b q I times 1 and minus b square q I epsilon. Okay, now this one is epsilon and this one is epsilon times epsilon would be epsilon square. So they are not really participating when they will all be concentrated here. And without them, we will have basically q1 plus epsilon I, okay, and this one and this one will cancel each other. So, I mean, it's a little trick, but it works. All right, so basically we can convert the whole thing into this. And what's the purpose again? Our purpose was to find out not just this, but how this thing is changing differentiation by epsilon. And now we are seeing that differentiation by epsilon is just this coefficient. Again, same as Taylor formula. So basically the whole thing would be differentiation of qi velocity of transformed by d epsilon would be equal to a minus b qi prime, where a is equal to this, the generator of spatial transformation, and b would be this, generator of time transformation. Now, the generator of coordinate transformation is basically the initial speed f we would calculate it. It's differentiation by t. So speed of change of transformed velocity is the same as speed of change of normal velocity by time. And this is some kind of a additional member related to change of time. If time was constant, if time was not changing, I would not have this member. I would have only a. But since time is changing as well as time with epsilon thing, that causes this additional member. That's a physical sense of it, basically. So again, we have derived the law how velocity is transformed in an infinitesimal. What's the rate of change of transformed velocity as we are changing the parameter of transformation. That's it. It's a little involved, but here is a very important thing. There is a note which complement each lecture, and in the notes I do it in maybe a little bit more details, getting basically the same result. And what I would suggest you to do is read the notes as well, which contain exactly the same thing, but you will definitely kind of conceptualize it much better probably after reading it with your own pace, whatever you decide. So basically that's it. Read the notes. You make sure that the whole website contains not only this particular lecture, but the whole courses. Course of Math, the 14th, course of Physics 14th, advanced course of Math, and this is basically advanced course of the Physics Plus. So enjoy it, and knowledge is power. Thank you very much, and good luck.